Hi everyone, in this lesson we're going to look at 7.7, which is complex numbers. And we're going to start out with the square root of -16. So if you were to simplify that, what would it simplify to? And if you're having trouble thinking of what it would simplify to, it's because there is no real number that simplifies to the square root of -16. If we were to think about what a square root is, you're trying to find a number that's squared will give you the radicand. And if you take a number and square it, whether you take +4 squared or -4 squared, both of them end up giving you 16, which is not the same as -16. So we have to look outside the real number system and look at the imaginary numbers. Both the real numbers and imaginary numbers are part of what's called the complex number system. So the complex number system includes the roots of negative numbers and the set of the real numbers as a subset. Okay, and this allows us to solve equations such as if we had x squared plus 1 equals 0, and we were to solve that, x squared plus 1 equals 0 is a quadratic equation. So if we were to solve that, if you try to factor x squared plus 1, you can't factor it. So one method that you could do is you could use what's called the square root method, and you could subtract 1 from both sides, and you would get x squared equals -1. And you would try to solve for x, so you would need to take the square root of x. And when you do that, you end up with the same problem that we started with. You get the square root of a negative number. So to combat that, we will call the square root of -1 the imaginary letter I. So really, x here would equal, we use a plus or minus, and then we have the imaginary number I. So I stands for the square root of -1. And I squared would just be -1. And the way you would get that is square this side, square that side. And as we know, when you square a square root, the square root symbol just goes away and you're left with the radicand, which would be -1. So these are two important things to remember, that I equals the square root of -1 and I squared is -1. So now in the first set of examples, we're going to write with I notation. So the square root of -36, you can actually break down into the square root of -1 times the square root of +36. And we're using the product rule for radicals. So the square root of 36 we know is 6, and the square root of -1 is I. So we would just write our answer as 6I. So now we can go back to the square root of -16, and we can break that down into the square root of 16 times the square root of -1. And we know that the square root of 16 is 4, and the square root of -1 is I. So we would be left with 4I for our answer. If we take a look at letter B, we've got the square root of -5. And there's not much to break this down, except that we can break it down into the square root of 5 and the square root of -1. Okay, and we know that the square root of 5 is just the square root of 5. You can't simplify that anymore. We know that the square root of -1 is I. So here we would have the square root of 5 and I, and we're going to write that as I square root of 5. In letter C, we have negative times the square root of -20. So really what I have here is a negative times the square root of 20 times the square root of -1. And we know that we can break down the square root of 20. That breaks down into the square root of 4 times the square root of 5. And the square root of -1 is just I. So I would have 2, and then I'm going to place the I next to the 2. So it's going to be 2I root 5, and then you're going to drop the negative down. So it would be -2I root 5. So now when we're looking at the product rule for radicals, it doesn't necessarily work the same way with imaginary numbers. So what we mean by that is if we were to take just the square root of 3 times the square root of 5, we learned in another section that you could use the product rule. Since they're both square roots, just multiply them together and you would get the square root of 15. Okay, it doesn't work like that with imaginary. So if I was to have negative, the square root of negative 3 times the square root of negative 5, you can't multiply those two together and get the same answer. So what we're going to do is first write each number in terms of I. So we're going to do what we did in the last example. I'm going to take the square root of negative 3, and we know that would turn into I root 3. And the square root of negative 5 would be I root 5. And now I can multiply. So I have I times I, which works just like x times x, that's I squared. And then I have the square root of 3 times the square root of 5. Now I can use the product rule, and that's going to give me the square root of 15. So if you'll recall, I squared is actually equal to negative 1. And we get that from here, okay, by squaring both sides. So anywhere there's an I squared, you're going to replace it with a negative 1. So this really would just turn into negative 1 times the square root of 15, which we can just write as negative root 15. In letter B, I'm going to do the same thing. I have the square root of negative 36, and I know that I can take the square root of 36, which is 6, and then I have an I. And the square root of negative 1 is also I. If I multiply these together, 6i times I get 6i squared. And again, anywhere there's an I squared, you would turn that into a negative 1. And 6 times negative 1 gives us negative 6. In letter C, I'm dividing. So again, you can't use the quotient rule. Excuse me. You can't use the quotient rule the same way that we used the product rule as well. So we're going to first break these down, and I'm going to have the square root of negative 125. Okay, so I'm going to have to make that the square root of 25 times the square root of 5 times the square root of negative 1. So we know that the square root of 25 is 5, and the square root of negative 1 is I. So right now this would be 5i root 5, and then divided by root 5. And the root 5s are going to cancel out, and you're left with just 5i. So as we talked about earlier, we're dealing with the complex number system, which we said is made up of the real numbers and the imaginary numbers. Okay, so they would be complex numbers that are not real. Complex numbers can be written in the form a plus bi. So the numbers we're familiar with, that we've been working with since we were really young, they're just all real numbers. But they're actually complex numbers. They just don't have an imaginary part to them. When you have a plus bi, the a is known as your real part, and the bi is known as your imaginary part. And it's easy to recognize this because the part with the I for imaginary, would be the imaginary part. The other part's the real. So if you take the number 6, right, 6 is real. There's no imaginary part. It's because it would be like 6 plus 0i. 6 is considered a complex number. You can write it in that form. If you have 1 minus 2i, right, you have a real part, which would be 1, and the negative 2i, which would be the imaginary part. Okay, and then real numbers are made up of other number systems like rationals, which are any numbers that you can write as a fraction or a terminating decimal. And then we have the irrationals, which are part of the real number system, Irrational numbers are non-terminating and non-repeating, so they go on forever and they don't repeat. Some classic examples of that would be pi and the letter e, which is known as Euler's number. So we're going to now take a look at complex numbers, and we're going to look at some operations. We're going to look at adding or subtracting them, and then multiplying and dividing. So what we know is two complex numbers are equal only if their real parts are equal and their imaginary parts are equal. Okay, so we're going to add and subtract by adding or subtracting the real parts and then the imaginary parts. So if I take a look at letter A, if I have to add these two complex numbers, 2 plus 3i is a complex number. It's made up of a real and an imaginary, and negative 3 plus 2i. I'm going to add the real parts together, which would be the 2 and the negative 3, and then I'm going to add the imaginary parts, which would be the 3i and the 2i. And 2 plus negative 3 gives me negative 1, and 3i plus 2i is 5i. In letter B, I am going to subtract 1 minus I, so I can distribute the negative. I would get 5i minus 1, and then negative 1 times negative I is positive I. And I'm going to combine like terms. I have the two imaginaries, 5i plus I, which would be 6i, and then negative 1. And if we want to write this in the form a plus bi, I'm going to rearrange this and put the real part and then the imaginary part. So my answer would be negative 1 plus 6i. In letter C, it's very similar. Here you have two negatives, which turn to a positive. You really have negative 3 minus 7i plus 6. Again, I have my two real parts, which I can combine. Negative 3 plus 6 gives me 3. And then I have minus 7i. And that's in a plus bi form. So that's adding and subtracting. To multiply, we need to remember that sometimes we're going to end up with an I squared. And when we see an I squared, we're going to want to turn that into a negative 1. So I'm going to put a red flag there to watch out. Anywhere there's an I squared, we're going to make it a negative 1. So you don't want to forget that. So we're going to multiply these complex numbers, and we're going to write our answer again in the form a plus bi. So here we've got negative 7i times 3i. Negative 7 times 3 is going to give us negative 21, and I times I is I squared. Okay, so here we have I squared, which equals negative 1. So I'm going to replace the I squared with the negative 1, and now I would get positive 21. In letter B, I'm going to distribute. So 3i times 2 would give me 6i. 3i times negative I is negative 3i squared. And again, anywhere there's an I squared, I'm going to turn that into a negative 1. So you would have 6i minus 3 times negative 1. And if I simplify that, I would have 6i plus 3. But I want to put it in the form a plus bi, so I'm going to rearrange that and make it 3 plus 6i. In letter C, you are multiplying two binomials. And when we do that, we want a FOIL. So we're going to multiply the first times the first, which would be 2 times 4. Then I'm going to multiply the outer terms, which would be 2 times I. And then I'm going to multiply the inner terms, which would be negative 5i times 4. And then I'm going to multiply the last terms, which would be negative 5i times I. Okay, so 2 times 4 is 8, plus 2i. Negative 5i times 4 is negative 20i. And negative 5i times I is negative 5i squared. Okay, we're going to make I squared negative 1. And of course, I can combine my like terms. Okay, So when I turn this I squared into a -1, -5 times -1 actually turns into a +5, right? So now I can also combine the 8 and the 5. So 8 plus 5 gives me 13. 2i minus 20i is -18i. And in letter D, you can FOIL this, or also notice it's a sum and a difference, right? Because I have both expressions are the same. So when that happens, all we have to do is square the first term, and then it's always going to be a minus, and then a square the second term. 7 squared gives me 49, and -3i squared would give me -9i squared. And remember, anywhere there's an I squared, you're going to turn it into a -1. So this actually turns into 49 minus 9 times -1. So this would really turn into a +9. And 49 plus 9 gives me 58. Please make sure you're taking the time to practice these problems as well, because the more you practice, the better you'll get at it. Okay, the last operation that we haven't talked about is dividing. When you divide, just like with radicals, you don't want to have any imaginary or i's in the denominator of a fraction. So sometimes we're going to have to use what's called the complex conjugate. If you'll remember back in the lesson where I showed you how to rationalize, let's say you had a problem where it was like 2 plus 1 plus the square root of 3. Okay, we don't like to have radicals in the denominator, so we rationalize it. And the strategy we used for that was to multiply by the conjugate, which is just take that same expression and just change the sign. So where we had a plus, we're just going to make it a minus now. And then you would multiply straight across top and bottom. And what would ultimately happen is the radical in the denominator would go away. So the same idea is used when you have imaginaries. You don't want the I in the denominator. So we're going to multiply by what's called the complex conjugate. And it's the same reasoning. It's just complex because we have an I now. So when we divide, again, we're still going to write our answer in the form a plus bi. In letter A, I have 2 plus I divided by 1 minus I. And we don't want the I in the denominator. So we're going to multiply top and bottom by the complex conjugate of 1 minus I, which would just be 1 plus I. And remember, to multiply fractions, you just go straight across top and bottom. So on the top, I'm going to have to end up foiling because I have two binomials. Okay, so if you FOIL the top part, 2 times 1, 2 times I, 1 times I, and I times I. And in the denominator, you're going to have 1 times 1, 1 times I, -1 or negative I times 1, and negative I times I. And if I look at the top part, I would have 2 plus 2i plus I, and then remember I squared turns to a -1. And then in the bottom, the i's cancel, and remember where you have an I squared, it turns to a -1. So now on the top, you would be left with 1. If you combine the 2 and the -1, you'd be left with 1 plus 3i divided by 1 minus -1 is 2. And if we need to write our answer in terms of a plus bi, we're just going to split this up, as we know we can from working with rationals. We're going to have 1/2 plus 3/2 I. In letter B, I need to multiply both top and bottom by 3i to get rid of the I in the denominator. So 7 times 3i gives me 21i. And in the denominator, I've got 3i times 3i, which would be 9i squared. Remember, I squareds would turn into a negative 1. So now you have 21i divided by negative 9, which we can reduce. 3 goes into 21 7 times, and 3 goes into negative 9 3 times. So it's really just negative 7/3 I. And as you notice, the i's went away in the denominator. The last thing we're going to talk about in this video is the fact that when you are looking at I to the first, I to the second, and so on, there's a pattern that occurs. So if you look, I to the first is I squared we know is negative 1, I to the third would be negative I. So if you think about it, I to the third is made up of I times I squared. I times negative 1 is negative I. And then I to the fourth is really just I squared times I squared, or negative 1 times negative 1, which is 1. And then the pattern starts all over again. It goes I, negative 1, negative I, 1. So after every 4, the pattern repeats itself. So if I want to find, say, I to the 20th, okay, you could, continue this pattern until you reached I to the 20th. But what if you had a big number like I to the 400th or I to the 1000th? How would you know what the answer would be? No one has time to sit there and figure it out. So what you can do instead is you can take the exponent and divide it by 4. And 4 goes into 25 times, and there is no remainder. So each of these powers, think of them as the remainder. If you have a remainder of 1, the answer is going to be I. If you have a remainder of 2, the answer is negative 1. If you have a remainder of 3, you would have negative I. If you're dividing by 4, the highest remainder you can have is 3. So think of this as remainder 0. Anytime you have a remainder of 0, the answer will be 1. So here, I to the 20th, since we have a remainder of 0, would just be equal to 1. And you can try it on the table if you want, because next you would have I to the 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th. And as you can see, you would end up with a 1. Okay, we'll try it for this one. I to the 46th, I'm going to divide 46 by 4. And I know that 4 goes into 46 11 times with the remainder of 2. So that means that I to the 46th is just going to equal negative 1, because that's what I squared would give us. Okay, now I have I to the negative 24th. So remember, when we're dealing with negative exponents, to fix it, we're just going to put it on the bottom. Okay, and we know that 4 goes into 24 6 times and no remainder. Okay, so that would mean I'm looking again here, and I know that 1 divided by 1 is just 1. Okay, that ends the video for complex numbers. Please make sure you're working on your homework and practicing. And if you have any questions, please reach out to me. Hope you all enjoy the rest of your day.